I want to present my recent work on building resilience in wireless communication systems with a secret key budget. And there have been talks about resilience before also at this conference, and it's a hot topic at the moment. And I think everybody means something different when they talk about resilience. So let me maybe start with a definition that I use as the basis of my work. And that is one that is given by NIST, so the American Standardization Institute. And they define resilience as the ability of a system to anticipate, withstand, recover from, and adapt to adverse conditions, stresses, attacks, or compromises. And for wireless communication systems, maybe not all of them apply or are equally important. But this is the basic definition that I use as kind of the foundation. And more specifically, I use this resilience cycle model, which you also might have seen before, which basically breaks down a system operation into these 4 distinct phases to kind of describe a resilience event or disruption or whatever you want to call it. So you typically have a normal state of operation, which is this blue state, where all your system parameters are within like specified boundaries. It's kind of what you expect your system to behave like. It should also be noted that you will still have performance fluctuations within this normal operation state, but that's just kind of the usual stuff. So nothing is perfect. You have noise, you have all of that going on. So even during the normal operation, there will be some performance fluctuations, and most of the system design that has been done so far in terms of countering noise, fading, all of that, you would probably consider to be within this normal state of operation. Then things might happen. So there might be an event, an emergency event, which triggers this alert state or emergency state, which is typically caused by external disruptions. And so people, I think, who have used this particular resilience cycle most are the guys working in power grids, or more generally in like network sciences, where, for example, the normal state is just kind of a day like this. Everything's working fine. Maybe some parts, some hardware of your system fails occasionally, but then you replace it, nothing. I mean, you as the user, you don't even notice. But then maybe there is a hurricane, an earthquake, some severe event which triggers this alert state, which severely degrades the performance of your system. So it wipes out power stations, power lines, like everything goes down. And after a certain time, this ends, and then your system stays in this state of degraded performance. Everything is down. And at one point, hopefully, you can send out some crews to kind of rebuild your system, and then you have this restoration process. And at one point, hopefully, you just are back to normal. And so I want to use this model also for basically the physical layer or the lower layers of a wireless communication system. And in my work in particular, since you cannot cover everything in one work, right? We focus basically on the normal state and this kind of transition to the alert state and how you can be prepared for that. Because ideally, you kind of anticipate these emergency events, at least up to a certain degree, and have your system be prepared for that, so they can at least either gracefully degrade or maybe just withstand this emergency event. Okay, and just to summarize, so with resilience, I mean external disruptions. So if we're talking about wireless communications, it's not about the fading itself. So the communication channel can stay the same also in these emergency events. It could change, but in this work, we assume it stays the same. So it's not a shift of the fading distribution, for example, but it's an external disruption. Typically, you would say these are rare and catastrophic events. And the parameters of your system are outside the spec. So that is one of the main differences. And especially with this preparation, there's the long-term perspective aspect, because since it's a rare event, you kind of expect to have a lot of time to prepare for this. So it's not that like every second time slot this happens. In contrast to that, we have reliability, which is discussed, well-known idea in communication systems, which, as I mentioned before, this typically concerns the regular performance fluctuations, noise in your system, fading, all of that. So this is not what we are talking about in this work. Okay, so as the title said, it's about systems with a secret key budget. So security, physical layer security is also an aspect of this particular work. And so the system model that we consider is just a very basic wiretap channel, so to speak. So you have your transmitter, Alice, your legitimate receiver, Bob. They are connected through this channel, which we now only characterize by this random variable X, which basically represents the SNR. And you also have a passive eavesdropper, Eve, and the channel Y, which is between Alice and Eve. And in order to transmit your messages securely, what we assume is that the receiver, the legitimate receiver and the transmitter use a one-time pad, which is known to achieve perfect secrecy. So that's kind of the reason why we do this. We want to have a perfectly secure information, theoretically perfectly secure communication. And the way you do this is very simple for those of you who don't know. So if you have a key, pre-shared key between Alice and Bob, which needs to be of the same size as the message, you just XOR the key with the message bit by bit. Then you transmit the encoded message, and then the receiver just does the same, XORs the received message bit by bit with the key, and then the message pops out again. And if they do this properly, and if it's a secure key, then Eve has no way of decrypting this message. One of the issues is, many issues, as the name suggests, one-time pad. You can only use the key bits once. And so if you reuse key patterns, then you lose this guarantee of perfect secrecy. So that's, and the other issue is that you need the key to be as long as the message. So if you have long messages, you need a lot of key bits, and you can only use them once. So that's kind of a shame. But so the way we deal with this problem is that we use wireless secret key generation, which is also a well-known concept in physical layer security. There are many protocols, many models how to achieve this. This is not really part of this work. We just assume they have implemented some SKG scheme perfectly, and it works fine. And so what they do in practice in this model is that Alice wants to transmit a message, so she uses keys from this key budget, which I will also explain in a minute, to encrypt the message, transmits it perfectly secure. Bob knows has the same key bits in the budget, uses the same pattern, can successfully decrypt the message. And then after that, they throw it away because they cannot reuse the key bits. But luckily, they can do this secret key generation to generate new keys and kind of fill up the budget again. And what we are interested in this case is how to optimize the transmit power for the secret key generation, because there's also this effect that if you increase the transmit power, you can, in general, generate more key bits securely. However, then you need to spend more power, which we also want to avoid, right? Okay, so just to illustrate this a little bit further, and I will also talk about the notion of the budget a little bit. But in general, you can just think about this budget, secret key budget, as a buffer. So what you have is you have a bunch of key bits in this. So let's say we start with 6 pre-shared keys. And then there's a time slot where Alice and Bob do secret key generation. They were able to generate 4 new key bits successfully in this case. And all they do is just append those key bits to both of their budgets. And then the number of available key bits after this first time slot would be 10. So this variable B basically just keeps track of how many key bits we have available. And then if a message comes in and Alice wants to transmit this securely, let's say there's a message of length 5 in this case, she just takes the oldest 5 key bits, XORs the message, transmits this secure code word to Bob, and then Bob uses the same 5 oldest key bits to decrypt the message. And then since it's a one-time pad, they have to delete them. And so after the second time slot, we are only left with 5 key bits that we can use for a new transmission. Okay, so this is the idea of this budget. So basically, you can think of it as a buffer. So you have incoming key bits if you do secret key generation, and then you lose key bits if you transmit messages securely. And in this work, we assume a very simple transmission model. So we assume that Alice only needs to transmit messages occasionally, maybe some status updates, which in each time slot arrive with a probability P. So basically, each time slot, we flip a coin with probability P. If it's heads, then there's a message, we transmit it. And if it's not, then the system is in some sense idle, so we can use those idle time slots to generate new key bits. And also we assume that all messages, for simplicity in this work, are of the same length L, which is given by the protocol. So every packet is a standard size. And for this, at least in this talk, we also assume that we can only kind of set the power for the secret key generation once in the beginning, and then it's a constant power in every time slot. We have also extended this already to a dynamic power allocation, because you also might want to adjust the transmit power based on the channel state information, for example. But for simplicity, we don't assume that we do this. We have a constant transmit power in this case, and we introduce in this for this notation the variable z, which is the usage of the key bits. So that's important. So it's positive if we use keys. For example, if in this case, if we transmit a message, we lose L bits. And then since the secret key generation part depends on the channel, it's random, it's a random quantity. So this fluctuates over time. And so now we're interested in this evolution basically of the secret key budget, right? It's kind of like, okay, how many key bits do we have available every time slot? And if you write it down, it's a very simple random walk. You start with like a certain number of pre-shared keys. And then every time slot you have this usage. So that's why there's a minus. And that just sums up to time slot. Time slot t. And then the z is, as I mentioned, so in the case a message arrives, we have L bits that we transmit. Otherwise, we do secret key generation, which is a random as a random rate. Okay, and now the problem is that we want to address in this work is what is the optimal transmit power for a given resilience requirement. And the next question, which is kind of the first one to ask actually, is how can we even quantify resilience? So that's kind of one of the contributions of this work, to actually make resilience specific, or at least one aspect of resilience, since there's so much talking about resilience without specific examples. So this work at least tries to provide some specific metrics, some specific ideas of how resilience can be quantified. And so to go back to this resilience cycle, what we do from now on is that we assume that these alert states are of a constant, of a random duration, capital T. So every time this alert state occurs, we don't know how long it will last, but we know the distribution of it. And it's characterized as this catastrophic event. So since there's some external disruption, Alice needs to update Bob every single time slot. So basically what it does is it sets P equal to 1. So we have a lot of important messages coming in every time slot that we want to transmit securely. And so this is kind of this shift from the normal state to the alert state, is that we need to transmit a lot of messages for T time slots. Okay, so how can we quantify resilience for this system? So we propose two new metrics for this. The first one is an alert outage probability, epsilon, which basically characterizes the probability that you do not survive an alert state. And by survive, we mean that the budget, so the number of available key bits, drops to 0. So the next time a new message comes in, we are not able to transmit it securely, which we call an outage. And the probability of that happening during this alert state is epsilon. Which is the probability basically that since we need to transmit for capital T time slots, L bits every time slot, that the budget that you have when you enter the the emergency state is less. So this is the survival probability. So it needs to be larger than this. And then also the second requirement means that you have survived until this point, because maybe your system died before, and then you cannot even enter this alert state. And the second metric that we introduce is the resilience outage probability, which is kind of a meta probability on top of that. which is basically the probability that this alert outage probability exceeds a tolerated level. So because everything is random, you could have very long alert states. There's always a positive, at least if it has an infinite support, there's a positive probability that you will not survive an alert state. And so this is kind of the meta probability on top of it. Okay, and then now the objective is, given these two metrics that we now introduced to quantify resilience, what is the minimum transmit power such that we can achieve a certain performance? And the solution that we used is basically borrowing tools from mathematical finance. And so that's also one of the key messages that you can oftentimes get good ideas from seemingly unrelated fields. In this case, it's basically insurance mathematics, because they have similar notions of risk, but for them, instead of like bits and packets, they talk about money. But we can kind of adapt the ideas that they use. And in particular, we use a framework or whatever you want to call it, which is called an area, which is called ruin theory, which basically deals with insurance companies and the likelihood of them going broke. That's kind of where it comes from. And so the first parallel between this ruin theoretic approach and our system is that insurance companies also see two opposing cash flows. So they have a budget, they have an amount of assets, and first they see incoming cash, which are the premiums paid by the customers, and sometimes those customers actually also want money from the insurance company. They don't like it, but sometimes it happens. Which are typically modeled as random claims at random times. And so if you look at the standard ruin theoretic model, it looks like this. So the number, like the total assets, the total cash that the company has some like starting capital, then they assume a constant income. So they assume constant premiums. And then they have these random claims at random times. So this NT in general is also random. Following some processes, some models, and that's kind of the basic assumption that they do. And if you compare this to our system, this looks already very similar, because we have these incoming cash flows, so to speak, which are the bits that we generate with secret key generation, and then we have the amount that we need to pay by doing the secure transmissions. And so the quantities of interest in ruin theory are the time of ruin, which is basically just saying what is the first time slot that our company goes broke. And then there's also, on top of that, the ruin probability, which basically is the probability that our company goes broke before time t, giving a certain start capital X, and then of course also some modeling assumptions for those quantities. And so with these ideas, and you see, I mean, yeah, they have like these random claims, random numbers, so it's a little bit different, but similar ideas. And so if you kind of use this as a baseline, you can apply this to our system model, and you can derive some bounds of the resilience outage probability, alpha, which are given like this. And you can, in this case, also find these ruin probabilities in here. And so this is 1 minus the ruin probability. So this is closely related, because we use kind of the same idea. And you can also derive some long-term behavior. So if we say that these emergency events are happening very rarely, we have a lot of time to prepare, then T can basically go to infinity, and we can see what happens long-term in our system. And what we notice is that there is a critical arrival probability P, which is given by this expression down here, basically the ratio between the average amount of key bits that you can generate in every time slot versus the total amount, basically also considering how many you need to spend, so the message length L. And if your P, if the message arrival probability is above this, so if they arrive relatively frequently for the system parameters, you can show that this resilience outage goes to 1, so that's terrible. But if your P is small enough, then actually you can you can have a long-term resilience outage probability less than 1, which is basically only dictated by this ruin probability, so kind of just by the normal performance fluctuations during the normal state. And so you can, in that sense, perfectly prepare for an emergency state, or as good as it gets. And so just to give you an idea what this looks like, we run some simulations, some numerical toy examples. You can find all the details in the papers. So this is just like Rayleigh fading and basic simple assumptions. And what you can see is here is, first of all, this limit, this upper bound, which is the probability of ultimate ruin. So this is this like infinite time horizon ruin probability, which is the red line, which we have shown in the previous slide, that that this alpha approaches this if you let go t to infinity. And in this example, as you can see, is less than 1. So the system parameters have been set such that this p is less than this critical value. And you can see this approaches it nicely. The blue curve is the numerically or Monte Carlo simulated resilience outage probability, and you can see that this indeed approaches the red line. And then the yellow curve is just the basically the finite time ruin probability at time t, which is a lower bound. And as you can see, of course, this also approaches the red line. And so this kind of is in between, and the blue line is in between those. So both of them are good bounds and close to the actual performance. And coming back to the original question, which was, what is the minimum transmit power such that we can get a certain resilience level? So for this, we now plot the resilience outage probability over the transmit power. And first of all, you can see in this case, we have shown the blue and the yellow curve at a specific time slot, which was t equals to 200. And if we let this 200 basically also extend to infinity, then actually the blue and yellow line would match the red line. So you can see for small transmit powers, there is still a big gap at time t 200. So the convergence also depends on that. But as a conservative system designer, you can just use this red line because you know this is the kind of the upper bound which will be approached. And so if, for example, you say you can tolerate a resilience outage probability of 10% in your system, if your application allows for that, then basically you can use these results to just kind of invert this line, this graph, and see that the minimum transmit power that you need to stay below this 10% mark is 7.5 dB. So if you have this constant transmit power requirement, then you could just use the results and set this to 7.5 dB, and then your resilience would be, or your resilience outage probability would be less than 10% in this case. Okay, so to conclude my talk, the secret key budgets can be used to prepare for emergency states. Maybe one more comment about why we called it a budget and not just a buffer. In this work, we assume that a message arrives, you immediately need to transmit it, and it's a constant length. So there's actually no flexibility. But in general, what we want to do in extended works is that you also have some flexibility on how to spend your secret key bits, because maybe you could have messages of different importance, and then sometimes maybe you want to drop a message, or you only need to encrypt parts of it. So this budget notion is basically to tell you that you have some flexibility also when spending the bits. So it's not like a message buffer where typically it's like, oh, you get a packet and it's just kind of stored for some time before you can process it, before you can service it. But this budget actually means that you have flexibility of like how to use it, when to use it, how to spend it, which we did not consider actually in this work, but you could. And also one other key message is that it's useful oftentimes to just look into other areas, what they have done, since you can draw like nice tools, frameworks from them. And so in this case, it was mathematical finance and insurance mathematics, which provided us this kind of framework and these ideas how to solve it. And if you're interested in this, there's a full version recently published, which also includes dynamic power control. So I've just shown you the results for a constant transmit power, which is the simplest case, where you can provide these bounds and everything. If you do a dynamic power control, then everything gets more complicated. and typically you have not really these nice closed form bounds, but they can have a better performance, of course. Yeah, so are there any questions?
Thank you for the very nice talk. I was wondering if you had any knowledge or intuition on what would change if you did allow your L, like your message length, to vary.
Yeah, that is a good question. We did not check that, but my assumption would be that basically this expression down here, this L would be replaced by the expected value of L, something like that, assuming there are no heavy tails and all that, which also probably wouldn't make sense. But yeah, so I assume most of the things will just be applicable, but some expressions might change. Like, yeah, for example, this will probably be the expected value of L instead of just L, but it should work. It should work, yeah.
Thanks.
Thank you. I have two questions. One question is general. Is it really about resilience in the sense from the first slide? It seems like it's normal operation, the system operated normally, and what is the probability that the number of responses will exceed the capacity of the system? It's where the unpredictable event is here.
Yeah. So basically from this definition, if we want to come back to this, what we kind of want to address is this anticipation and the withstanding, basically, to stresses or adverse conditions. And what the main difference is that it's so the communication system itself basically doesn't change. We just have an external disruption, which could be of any kind, which just triggers this emergency state. And we do, in that sense, a worst case assumption, since we require the system to transmit a message in every single time slot, which is, it cannot get worse than this. I mean, sure, you can always say, like, oh, the whole system breaks down and everything like crashes and you cannot really communicate anymore, but that's not really what we are. I mean, that's kind of the super pessimistic view. But assuming that you can still operate the system, this is basically the worst case that could happen is if you have to transmit a message securely in every single time slot. So that's kind of in that sense, you do need to make an assumption to make some meaningful or get some meaningful results. Yeah.
Okay, thank you. And the second is mathematical question. Could you switch to slide 12? About with this probabilities epsilon and alpha. Could you please repeat once again?
Yes.
So if epsilon is already a probability, so it seems that epsilon is not a random variable. Why do we say in the next formula again about a probability? What is random in remains in epsilon?
So epsilon. Okay, so epsilon is a probability, which quantifies that if you basically enter at time t, enter an alert state, what is the probability that you survive this alert state?
Yes, and epsilon seems to be already a non-random variable, but then in Formula 4, we ask about probability for epsilon being larger than fixed value. Then it seems that epsilon is still a random variable. So what is random in epsilon?
Yeah, that is a good question.
Okay, we can.
Yeah, we can take this offline. But yeah, there was. I need to check again, but there is randomness in epsilon basically on every time slot. Depends on the realization, because you can have different realizations of that. Yeah, but we can take it offline.
Okay, so maybe in Formula 3, formally one can, depending on what do you mean, like a not a conditional probability, something like conditional expectation, which is still a random variable, and then we get a final.
I think that would probably be more accurate. Yes.
Okay.
Yeah.
Okay. Thank you.
I have a question. So maybe I missed this part, but so you talked that the secret key is shared between Alice and Bob, right?
Yes.
So yeah, my question is like, so what happens if Eve eavesdrops into this channel where there is?
Oh, so she does. So the secret key generation protocols, they assume that you have this wiretap channel. So it's the same channel model. And then this is why also this secret key generation rate is a random variable, because it depends on both the realizations of X and Y. And then there's some, depending on the protocol and the model that you use, you get some expressions basically for this capacity. So it is also, it depends on the eavesdroppers channel. Yes.
Okay.
Yeah. So during the secret key generation, Eve is also present. It's just that these protocols, they also make sure that Eve is not able to infer any of the key bits. So it's actually a secure generation of the key bits.
Okay, so it's part of the secret key generation then.
Yeah, exactly. So the secret key generation takes place over both channels X and Y, so to speak. They are still present.
Yeah, thanks for the clarification.
Are there any more questions? If not, last question.
Thank you for the very interesting talk. I have a simple question that, so in this figure, there are two parts. First is key generation and then the key consumption.
Yes.
So I'm thinking the framework can also be applied to different ways of key consumption. Of course, that will lead to a different dynamic of your resilience. For example, here, this is one pad, and we can use, if I'm correct, so Anton has mentioned maybe yesterday or 2 days ago, if using AES, then we can use a shorter key compared to the one-time pad, for example. Of course, then, so that would be my question. So, for example, your framework can also be applied to that or not?
Yeah, sure. You could also use them as kind of seeds for other cryptography. Sure, but then you just need to adapt basically this secret key usage. Then you wouldn't have always this L.
But then that will lead to a new question. So because AES is based on this complexity-based secrecy, but your key generation is by physical security, if I'm correct.
Yeah, then you would lose the perfect secrecy in general if you just use any other.
Or they are different secrecy metric.
Yeah. Yes.
Yeah. So if we want to uniform them, maybe, for example, the key generation will follow this semantic secrecy constraint, like Igor has.
Yes, you could sure. You could kind of, that depends on your system assumptions or application. If we just assume that we need this perfect secrecy for every message, which is also a very strong assumption in general. But
So if, for example, if semantic secrecy is used, then that will guarantee, I mean, that is stronger than, for example, AES, then that will have a consistent secrecy representation compared to if we arbitrarily use some secrecy constraint in physical security, but the encryption part is complexity based, that will be hard to, it's not comparable.
Yeah. Yes, that's true.
Thank you very much.
Also, maybe one more comment. Of course, you could also, this is just one example of this, an example application of this idea. But of course, you could also think of this, for example, as a battery. So instead of having a secret key budget, this could also be a battery. And maybe you don't have an eavesdropper in that case, but it's a battery. Then you have some energy harvesting to kind of get some of the battery back. And then you have the transmit power to transmit messages, regular messages without the secrecy constraints, which would still be kind of the same model overall. We have these two opposing cash flows, so to speak.
Yeah, that's very nice. Very general model.
Yeah.
Thank you very much.
Thank you, Karl. Let's thank the speaker again.